because quantum mechanics, as we currently understand it, is, well, as Einstein and Schrödinger said about it, it's an incomplete theory. I'm not as polite as they are. They were saying it's incomplete. I would say it's actually not even quite correct. And it's not correct because quantum mechanics, as it currently exists, does not have a theory of the collapse of the wave function. Now, you see, you have in standard quantum mechanics, you have the description of the world according to a thing called the quantum state. The quantum state evolves according to the Schrödinger equation, which is a deterministic equation, completely computable as well. However, it is not the way that the world evolves. As long as your system is small, in some technical sense of the word, small, then it does behave according to the Schrödinger equation. But when the system gets too big, and I could be more explicit about what I mean by big, when it gets too big, then it doesn't follow the Schrödinger equation. You have this phenomenon of the collapse of the wave function. And my argument is that it's not just that quantum mechanics is important for consciousness. Quantum mechanics on its own wouldn't give you consciousness. It's how quantum mechanics has to be extended to a better theory. As it exists, it would not explain consciousness. Quantum mechanics follows the Schrödinger equation, and following the Schrödinger equation doesn't give you what I need. You need something which goes beyond that, which is not computable. And the argument has to be in the collapse of the wave function. So I'm arguing it's worse than quantum mechanics, if you like. I'm saying what has to go on in the brain, in the conscious being, whatever its brain is like, that has to be something which is not just evolving according to current quantum mechanics, it's evolving according to that theory we don't yet have, which is the more complete theory in which the collapse of the wave function is part of that theory. So that needs to be there. And current quantum mechanics doesn't have a theory of the collapse of the wave function. I would say the collapse of the wave function is a physical process which is a long way away from explaining consciousness. And the physical process is something one can get towards. I have arguments, which I put forward quite a long time ago, to show that the two great theories of 20th century physics, or the two great revolutions in physics, were A, quantum mechanics, which came first, and B, Einstein's general theory of relativity. And what I'm saying is that those two theories have an incompatibility. Quantum mechanics is based on the theory or the basic principle of superposition. You can have a particle in one location, that's one quantum state, or it could be another location, that's another quantum state. And according to the basic principle of quantum mechanics, you can have states where it's there and there at the same time. So you have all these superpositions between different alternatives. And that's very fundamental to the framework of quantum mechanics. And the fact that you don't see most of these superpositions is not explained by quantum mechanics. Now, on the other hand, general relativity has its basic principle, which is the famous, Galileo-Einstein principle of equivalence. Well, Galileo explained it very well. Imagine dropping a big rock and a little rock from the Leaning Tower of Pisa, and he knew that air resistance would make a difference, and a feather would drop more slowly. But if you had no air resistance, they would fall completely together. So as they fall, there is effectively cancelled out gravity. So gravity is the one force, if you can call it a force, which I'm a little bit dubious about. It's the one feature of physics which you can cancel by free fall. And that feature is incompatible with the principle of superposition. And you can make a little argument to show that they're inconsistent with each other. And to make them consistent with each other, you have to introduce this collapse of the wave function. It also gives you a measure of how much, when do you expect the collapse to take place? And it's not a complicated formula. There's a formula I produced, which was actually not original with me, because Ayash Diosi had already found this formula about 2 years earlier than I did. I wasn't aware of his work, but I had this particular argument to show that his estimation of how long it takes for the wave function to collapse is in accordance with what my argument. Now, if I have an object, a big object, say like this magnifying glass of mine, and I put it in a superposition of here and here, that superposition would not last, well, it'd be a tiny, tiny, tiny fraction of a second. If on the other hand, it's a carbon atom or something, and here, well, it would probably, that superposition would last for longer than the age of the universe. So but there is a genuine formula which you can write down, which tells you how long that superposition would be expected to last before it collapses to one or the other. And it has nothing at that level, nothing whatsoever to do with consciousness. It's a physical formula. It's something which could be measured in experiment. It has not yet been, because experiments as they exist have not quite reached the level of sophistication in order to do this. There are experiments which are currently under being done. I mean, they're not there yet, but they're aimed at looking at this effect. And my hope is that they will see this effect when they get a little bit more sophisticated than they are just yet. And it won't be too long. When I say not too long, probably within the next 10 years. You have to have something which looks more or less like the classical world. And if you don't have the collapse of the wave function, the quantum evolution of a state does not look like the classical world. It just doesn't. I mean, there are arguments which people use, which are sort of approaches to this, but you can look carefully at these arguments and you see they don't do it. You have to have a development of quantum theory which has not yet been formulated as a complete theory. All I can do is say the level at which I expect collapse to take place. I say the collapse, if you have a physical situation where the parameters are so-and-so, then I might expect the collapse to take place within 10 minutes, say. And that calculation could be done. But it doesn't tell you exactly when it happens. It doesn't tell you which way the collapse happens. It doesn't give you a mechanism for collapse. It's just a formula which tells you how long a system can remain in superposition before it collapses to one or the other. And the connection with consciousness, you see, in my view, is quite secondary. And it's very important. I think I would certainly agree with both of you that it's very fundamental in the way the universe operates. Consciousness is playing a big role. But it's a subtle role, and it doesn't reveal itself until you have elaborate systems like living beings. As I'm aware, animals, maybe for all I know, plants might possess it to some degree. But I don't see it in inanimate objects. They're not sophisticated enough somehow to take advantage of the collapse of the wave function. But for them, it's just a random process. I think, Franz, there's one confusion here, which I think I'd like to get rid of in a way. See, in the early days of quantum mechanics, people worried about the collapse of the wave function, but not thinking of it as a physical process. I mean, many people, including most particularly Wigner, I think, because I talked to him quite a lot when I was in Princeton. I had conversations with Wigner, which were very interesting. And he had the view, as many others did, that somehow the collapse of the wave function was an effect of consciousness. That is to say, the terminology in quantum theory is very much suggestive of that, because it says you make an observation, and this observation induces the collapse of the wave function. Now that you see, it's rather suggesting that the collapse doesn't take place unless a conscious being comes along and looks at it. Then that measurement that the conscious being makes by looking at it, if you like, collapses the wave function. So it's as though it's the consciousness which causes the collapse of the wave function. That's very different from my view. It's almost the opposite of mine. In my view, is saying, no. It's not that consciousness causes the collapse. The collapse would take place quite independently of whether they're conscious beings or not. It's because the collapse of a wave function is a physical process which takes place when things become large enough, superpositions become large enough, in a way which I could be very explicit about if necessary, what I mean by large enough, and it would collapse the wave function quite independently of conscious beings. Whether you see there is a very important development in my thinking which I don't quite know when I first thought it, within the last 5 years, I would say certainly. I think the first thing I ever talked about, there was a conference in Arizona, I think, the idea, but it got developed since then. That you can't talk about reality quite like that. There are two kinds of reality. There's quantum reality and classical reality, and they are not quite the same. And quantum reality behaves in a way which is quite strange. Um, it's the notion of quantum reality actually comes from Einstein in a certain sense. He talked about a quantum state. He said, is the quantum state real or not? And a good example is the spin of a spin half particle. I take an electron. Now, the spin of an electron, the different possible spin states are spin right-handed about all possible directions. So I can move my thumb about the axis, and it spins right-handed about that axis. Now, all those different possible states, those are the possible spin states of an electron. Now, what you can't do is ask the electron what your spin state is, or you can try, but it doesn't give you any answer, because that's a quantum reality. However, if you do have a theory which says by now the electron ought to be spinning, say, about that particular direction, and it has all about the same amount, that's an electron, it's always the same amount, about that direction. Now, what I can do is I can confirm it. And this is Einstein's criterion. I can say to the electron, I'm going to measure the electron spin in that direction. And if I have it right, it will say, yes, you got it right with 100% certainty. And it will not disturb the system. You can measure it again and again and again. And each time it says yes. If I measure it in a different direction, it will give you a probabilistic answer. It will maybe say no, maybe yes, depends on, you do experiment many, many times, and we'll give you different answers. Now, the quantum state is something you can confirm in a sense, but you cannot ascertain it. You have to make a distinction between confirming and ascertaining. Ascertaining would be something you say, hello, state, which way are you spinning? It doesn't answer questions like that. But you can explain these rather puzzling things, which is what Einstein was worried about, in fact. These things called Einstein-Podolsky-Rosen experiments, where you can have a spin state which is shared by two observers or two people, let's call them, widely separated. And you know what the total spin, each one has a spin half particle, which has come from a spin zero initial state. And so they have to be opposite each other. Now, if one of the individuals measured the spin in some direction, that instantly makes it the opposite, actually worse than instantly. It goes backwards in time along the past light curve. And the other one is fixed by the measurement made by the one. And the other one, if that other one could ascertain what the state was, you would then have a contradiction. You could send signals faster than light. But you can't send signals faster than light. It would lead you into contradiction with relativity. However, what you could do is confirm that state. If the other person knew what the measurement the first one had made, then that measurement could be confirmed. But it cannot be ascertained. And if you could ascertain it, you could send signals faster than light, which would lead you into real trouble. Relativity wouldn't work, it would be real trouble. However, you can make the quantum reality of that state is projected backwards along the past light curve, so it goes not just simultaneously, but even back in time. But since that's only quantum reality, you cannot ascertain what that state is. So you have to make a distinction between the quantum reality, which cannot be ascertained, but it can be confirmed. Classical reality can be ascertained. So you can ask the state what it is, and it tells you what it is. So that distinction is something which has to be made in order to talk about reality. So reality, when you talk about quantum mechanics, the notion of reality, you've got to be careful about it. It's not like classical reality where there is only one notion of reality. Quantum reality is not reality in the sense, see, that's the trouble. If you turn word for reality, then you lead to a confusion like this.